Okay, we can let this homework act as the quiz review that we have on this material. So for number 1, which we started in class today with the green class, E2 period, we demonstrated how we rewrite this integrand so that we have the ability to just use the power rule for this integration. So if we do the integration now, we are going to get, I always said, just leave the coefficient as it is, increase the power to its new power, so x squared becomes x to the third, and then you're dividing by 3, which is like multiplying by 1/3. We move on to the next term, leave the coefficient out in front, leave yourself a little room. I'm going to increase the power to the second power, and then I divide by 2, which is like multiplying by 1/2. And then lastly, we have a -3. We're going to increase the power to -1, and then divide by -1, which is like multiplying by 1/-1. Put a plus c, and now all I need to do is go back and clean up. Well, in this first term, I've got a 3 and a 3 that can cancel, so it's just going to be 1/4 x to the third. Then in this second term, I've got a 4 and a 2, which can reduce to a 2 in the numerator. So I'm going to have minus 2x squared. I've got a negative and a negative in the third term, so that's going to become plus 3x to the negative first, and then plus c. And there's my answer, so I can just do that. We're good to go. So numbers 1, 2, and 3 here should be very straightforward. Don't waste any time. Quickly rewrite the function so that you can use the power rule. Increase the power, leaving some room for your reciprocal of your new power to go in front, and then just clean up your coefficients by reducing reducing any common factors if you can. If you didn't follow along in class, here's the answers to 2 and 3. 4 is essentially the same question, only that you've been given this condition that when x is 2, the y value is -3. So this notation means the y value when x is -2 is -3. So we separated the variables. We put the dx's over here with the x's. We got dy equals 6x squared minus 2x dx. Integrated both sides, put a plus c here, and then we went and used our what's called our initial condition that when x is 2, y is -3. -3 went in for the y, 2's went in for the x's, and we just simplified and found that c is -15, and then you just rewrite the general antiderivative with the specific constant thrown in, and that's your solution. On this second page, we were looking at definite integrals, so now our answers, rather than being a function with a plus c on the end of it, so I wrote here no c, we're going to have a numeric value, and that numeric value that we get for this thing is going to be the area bounded by this curve between these two limits, 0 and 1 in this case, 0 and 4 in number 6, and 0 and 1 in number 7. So again, this first one was all set to go to use the power rule, increasing the power by 1 and dividing by the new power. It simplified very nicely. It's going to be evaluated between 0 and 1, so we plugged in the upper limit, 1 cubed minus 1 squared plus 1, and then subtracted what we got when we plugged in the lower limit. Plugging zeros into these things always just gets you 0, so our answer was 1. And essentially what that means is the region bounded by this curve between 0 and 1 is 1 unit. So whatever that curve looks like, it would look something like that. Actually, I think it would be more likely that it would look something like this and come up and go down like that. So that would be 1 square unit of area in there. Anyway, moving on, we did the same thing with number 2. We first had to rewrite x to the square root of x as x to the 1/2. Then we performed the integration, plugged in the upper limit, and subtracted what we got when we plugged in the lower limit. Same thing with number 7, definitely the one that has the most going on. We had to rewrite this. Notice I rewrote the cube root of x is x to the 1/3, simplified each term, then increased the power to its by 1 and divided by the new power. What makes this one kind of manageable is the limits are 0 and 1, so you're just plugging in 1s into this thing and subtracting what you get when you plug in 0s. Plugging in 1s, we had to get a common denom of 40 for the 5, the 8, and the 2, and did that, and we got 57/40. So, 3 levels of difficulty, very easy, a little bit harder, and a little bit more complicated from 5, 6, and 7. And now lastly, with the last page, number 8, we kind of added a part B to this. The first part was just find the area bounded by this curve between -2 and 2. There's no need to draw this graph. Whatever the question is, you're just going to integrate this function between the limits. So what we did, though, is we found that the integral from -2 to 2 of this thing turns out to be -x cubed over 3 plus 4x between -2 and 2. But looking at it, having that upside-down parabola from -2 to 2, we realized that the region on the right side in green is exactly the same as the region on the left side. So what we decided to do is just find the region on the right side, integrating from 0 to 2, and then doubling it. So you see that here, 2 times the area from 0 to 2. And the reason we did that is because the simplicity of being able to plug in 0 as a lower limit is going to make the evaluation of this thing much easier. So we had 2 times what we get when we plug in 2 minus what we get when we plug in 0. So we got 2 times -8/3 plus 8, which is 2 times -8/3 plus 24/3, and we got 2 times 16/3, which is 32/3. So that represents all of the area that I had marked in class as region 1 and region 2. For part B, it said find the average value of this function. This function goes pretty quickly up here and spends a lot of time up here at these upper values, and then it comes back down quickly on the other side. And the way you find the average value of a function on an interval is just take the integral of that function on that interval and then divide by the width of that interval. So the integral we had already done. So again, that's a huge advantage. You don't have to redo this integral. You just did all that work to get it. So it's that 32/3 divided by how wide the interval is. Well, the interval goes from -2 to 2. So technically what we're doing is saying, well, how wide is it from here to here? Well, it's 2 minus -2, and that is 4. So for example, if I went from 3 to 10, the width of that interval is 10 minus 3, which would be 7. Now, of course, I don't think anybody needs to do that arithmetic. They can just tell that it's going to be 7. But if I went from, say, -5 up to 3, well, the length of that interval is 3 minus -5, which is 8. So this would be 8 units. So that's where that 4 comes from that's in the denominator right there. And again, you're just dividing the total area by the total width, and you get the average height. 8/3 would be fine. I wrote it as 2 2/3, so we could kind of picture what it would look like on our graph. Okay, lastly, and this will represent a lot of points on our quiz tomorrow because it really encompasses everything about the fundamental theorem of calculus, this idea that if you integrate a function and get a new function, the derivative of that new function is that is that integrand. So if you integrate f to get g, you take the derivative of g to get f. And for what it's worth, let's make sure that's really clear. If g is the integral of f, then g prime equals f. And if we need it, information about the second derivative of g would be given by the first derivative of f. So these are like the y values of f. So if I ever need a slope of g, if I need the slope of g prime, I just look at the y values of f. So in class, I said, what would g prime of 3 be? If I knew what the function g looked like, what would its slope be at x equals 3? Well, at x equals 3, the y value of f is -2. So we could say g prime of 3 is equal to f of 3, which is just -2, which means whatever's happening with g at the time, let's say g looks something like this. At x equals 3, that slope right there at that instant would be -2. That would be the slope of g. And again, if we have any questions about concavity or second derivative stuff, we can do that by looking at g double prime, which of course would be the derivative of f. So start with g, its derivative is g prime, its second derivative is g double prime. But g is equal to the integral of f, so its derivative is f, and the derivative of that, of course, is f prime. So we looked at, we gathered all the area that we could as we moved across the x-axis, and we got these little red and green sections. Now notice, everywhere that's red, that means g is kind of like a decreasing function. G is gaining negative area. Everywhere that we have red stuff, that's where the f is below the x-axis. So think about it. F is below the x-axis. That means the slope of g is negative, and that means the function's decreasing. The function g would be decreasing. the places where f is positive, everywhere in the green, that means if f is positive, the y values of f are positive, that means the slope of g is positive, which means g would be increasing. So we can just, kind of on that note, we can go and fill in some answers here. When is g increasing? I would say it's increasing during those positive f values that happen between -2 and 1. So we can put -2 to 1, that interval, and then it's going to happen again, you say in union with or together with, when you're over here between 4 and 6. And we could say because g prime, which equals f, is positive. That's the only verification you need to use for that. Now, when is it decreasing? Well, we're going to be looking for the areas where we have red area. That means g was picking up negative area, which means g's value is getting smaller. G prime is negative when f is negative. So between -3 and -2, and between 1 and 4. So let's put that in here. So what did I say? Between -3 and -2, and then again between 1 and 4. And we just need to say that g prime, which is equal to f, is negative there. Now, let's go back to item K, which says, where's the absolute maximum and where is the absolute minimum? It actually says what is. It doesn't say where is. I could ask you both of those questions. Well, if you think about it, absolute maximums happen either at endpoints. So if you have a graph and you do something like this, it comes up and it goes down, bottoms out, and then it comes up here, something like that. The absolute minimum either has to be at a local min, like this guy, or at one of the endpoints. Likewise, the absolute max has to happen either at a place where the slope is 0 or at one of the endpoints. Now, seeing this graph is really easy. This is the absolute max, and this is the absolute min. We don't see the graph of g, we see the graph of its derivative f, but we've got all this information about the endpoint values of g at 0 and pi plus 2.5, and we have places where the slope is 0. -1, 1, and 4. Those would be like the critical numbers, these three spots here, -1, 1, and 4. That's this place where the derivative of g, which is f, equals 0. So let's take a look at that. Absolute max is either going to happen at one of the endpoints, 0 or pi plus 2.5. Well, this guy's bigger than that guy. So far it's going to be 6 is where our maximum is going to occur. Or it could happen at this local max right here, where our slope went from positive to negative. Now, what's the y value at 1? At 1, we are at pi. So our candidates are the endpoints and the local maxes. Well, if you look at these three, the first option is the y value is 0. The next one is pi, and the last one's pi plus 2.5. So you just pick the biggest of those, which of course is pi plus 2.5. And that's our answer. So our absolute maximum value is pi plus 2.5, and that happens at x equals 6. Now the absolute min, same idea here. We can think about any local mins, like this guy here is a local min because our slope went from negative to positive. So -2 is a potential local min, so that guy, and there's a potential absolute min. We got to, again, look at the endpoints. So we're going to be considering 0 and 6. And then do we have any other local mins? Well, we have this spot here at 4 where we went from a negative slope to a positive slope. So at 4, let's check our y value. Let's mark him in red. Here's 4. So we have to compare the y values at all the red guys. So we have 0, -1, so 0 is out. -1 is our smallest one so far. Then we have pi minus 3. Well, is that going to be smaller than -1, or is -1 going to be smaller than that? Well, pi minus 3 is about 3.14 minus 3, that's going to be around 0.14. So that's a positive quantity. So -1 so far is our smallest y value. And then we check the last one, our endpoint, and it's not going to be that because that was our absolute max. So there is our absolute min occurs at x equals -2. So the absolute min is at, occurs at x equals, let's see, it was -2, and the y value there was -1. So that's our absolute minimum value, and it occurs at x equals -2. Now we can move on to this question about concavity to fill in this stuff down here. So for concavity, you're always thinking for g to be concave up, we're thinking the second derivative of g to be positive. Okay, that's when we think concave up. Now, the second derivative of g is given by the derivative of f, which I'm just going to write in here, is the slope of f. So we can look at f, this picture that we have, and you can see f has a positive slope here because it's going up, and it's going up, and it's going up. So the slope of f is positive between -3, x equals -3, and 0, okay? And so those are going to be places, and I'll just go ahead and draw on the graph there. This blue are the places where the slope is positive. So that means we're going to be concave up. So that's from -3 to x equals 0. So from -3 to 0. Now it looks like it's going to happen again from here all the way up to there. So that's more areas where f has a positive slope. And that looks like it's from 3 to 5. So now our reasoning can be g double prime, which equals f prime, is positive. Or you could say f is increasing, because to say f is increasing is the same as saying its slope, f prime, is positive. So you should be able to guess this now. When is g going to be concave down? Well, that's when f has a negative slope. So that's when g double prime, which is the slope of f, is going to be negative. So let's draw in our negative slope, which is from, oops, let's get that going on here. This stuff, that's all that red portion there, and then this last little red portion there. So that's between 0 and 3, and between 5 and 6. Because g double prime, which is equal to f prime, is negative. Or we could say because f is decreasing. What would be wrong, though, is to say f prime is decreasing. F prime is the slope of f. All we know about f prime is that it's negative. We can see negative slopes. We don't know they're getting more negative. And then lastly, inflection points. The easy answer to this is inflection points occur at the extrema, the maxes and mins, of the first derivative. So our maxes and mins are here, here, and there. But notice, those are places where f double prime, I'm sorry, where g double prime, which is f prime, changes sign. Look at the blue, f has a positive slope, then it has a negative slope. Then it has a positive slope, then it has a negative slope. So it changes, g double prime, or f prime, changes sign at x equals 0, x equals 3, and x equals 5. So we can just write that here. X equals 0, x equals 3, and x equals 5. And if I asked for a reason there, we could say because slope of f, or g double prime, changes sign at these x values. And there you go. That's everything we need to know about a function, looking at the graph of its derivative.